Hi everybody, my name's Cameron King and today we're going to be looking at energy, specifically energy and work, potential and kinetic energy, as well as power and efficiency. So let's start by looking at the law of conservation of energy. Now you might have heard about the law of conservation of matter. This is similar. Energy cannot be created or destroyed. It is only transferred or converted into other forms of energy. Okay, so when we think of an example about this, it will be something like a car slowing down. Okay, the energy that is making that car initially move is not being destroyed when the car slows down. It is merely being transferred into the environment, either as heat or as sound. Okay, and that is how energy is conserved in that entire system of the car making contact with the road and the car in the air around it. Energy is being conserved in that system. The total amounts of energy is not changing. Okay, so let's look at the different types of energy. So we mainly have potential and kinetic energy. Okay, now potential energy can include gravitational energy. So this is stored energy due to an object's position. Okay, if something is on the ground and it cannot fall, its gravitational potential energy, the potential for the object to move, is going to be at zero. But as soon as we start lifting it off the ground, the potential energy, the potential that that object has to move is going to increase. Okay, it's important to know that potential energy is energy in stationary objects, objects that are not expressing their energy, but they have the potential. It's stored inside of them. So there's gravitational. Another one is chemical energy. Okay, this is stored in chemical bonds. This can be something like food, like batteries, wood from a fire. Okay, it has stored chemical energy. That's measured in joules as well. So like our food, let's say, if you look at the back of a food wrapper, it'll say the amount of kilojoules in that food. Okay, that's how much stored energy there is in that food. And then finally, we have elastic potential energy. Okay, if you've ever been hit with an elastic by someone, or if someone takes an elastic to you and stretches it back, you're going to flinch, okay, without it having hit you. And that's because you know that as that elastic has stretched out, the distance between the points has increased, and just like gravity, that has the ability now to move and move really fast and hit into you and hurt you. You see, so these were potential energies. Okay, now moving on to kinetic. In kinetic energies, we have objects that are moving, objects that are in motion. Okay, their energy we can say is being expressed. It is being transferred, let's say, into the outside world. The first one is mechanical energy. So this is energy of an object in motion. Okay. The next is thermal, sound, or radiant energy, also measured in joules. Okay, this is energy of the movement of heat, sound, and light. Radiant means light energy. Okay. Finally, we have electrical energy. So this is energy of the movement of electrons. Okay, when electrons move, they're going to create energy. Okay, we're going to get into that a bit later when we do work and energy. So as I said earlier, when we transfer energy, okay, from one form to another, we say this is work. Okay, so work is done when energy is being transformed. Okay, and there's a equation for work and how to calculate it. So work is measured in joules, okay, and it equals to the force in newtons multiplied by the displacement, how far the object is moved from its original position. And your force needs to be in parallel to the direction of the motion, which makes sense. Okay, when a force is applied to an object in a certain direction, the object's not going to move backwards, it's not going to move up, it's going to move in that direction. Okay, and displacement is if the object is having the force acted upon it in a angle. Okay, so let's say you are pulling a box, okay, but you're not pulling that box like this, you're pulling it slightly up, but it's still moving, okay, you're going to take that movement as the displacement in that certain direction of motion. And you calculate it using that cos theta. So, as we said, work is done when energy is transferred. So that means friction is a good example of where we can see work being done. Friction we know as something like rubbing your hands together. Now what happens when you rub your hands together? They start to warm up. That warming up shows that work is being done because there is friction. Energy is being transferred from your hand movement into your skin, let's say, and then from your skin into the air. Okay, but work is being done. Now there's two types of friction. There's static friction and kinetic friction. Static meaning non-moving. Okay, so if it's static friction, it's the friction we need to overcome to have an object start moving. Okay, this is usually going to be the friction between the object and whatever surface it's on. Okay, whereas kinetic friction is the friction that needs to be overcome to have the object continue moving. This could usually be something like air resistance. Okay, if air resistance is stronger than the force being put into an object or the work being done by the object, then the object is going to stop moving. Okay, so kinetic friction is the friction that needs to be overcome to keep it moving. Okay, so quickly just looking at gravitational potential energy and kinetic energy again. Okay, we know the definitions. Okay, so gravitational potential energy is the energy held by an object because of its position relative to other objects. Other objects could be something like the floor. Okay, now the equation we use is mass times gravity times height. Mass in kilograms, gravity in newtons, and height in meters. Okay, you must really understand your conversions between, let's say, grams and kilograms, okay, and the different forms of distance measurement. Okay, because in a test they might give you it in millimeters, or they might give it to you in grams, okay, or they give it to you in kilograms. You must know to use kilograms then and not convert it to grams, okay. And then, so an example, again, like a roller coaster on top of a hill, okay, or someone on top of a building, okay, something like that would be gravitational potential energy. Now, kinetic energy is the energy of movement. Okay, kinetic energy would be half mass times velocity squared. Don't forget that squared. It'll mess up your calculation completely. Okay, mass, again, in kilograms, velocity in meters per second. Okay, and this would be something like a roller coaster. As it reached the top of that hill, coming down, and at the bottom of that hill, its kinetic energy is going to be at the maximum because that's the fastest it's going to be going. Okay, so as we see here, an example of potential turning into kinetic, okay, but the total amount of energy stays the same, okay, throughout the system. Now, there's no friction force here, but if there was, then there would be an increase in thermal force as well. And our total energy would decrease as it goes into the environment. Okay. Now, we also mentioned that you can get elastic potential energy. Okay, so work is done anytime we stretch or release a spring, okay, a rubber band or a bowstring, something like that. Okay, and it is going to be measured as half the spring constant multiplied by the extension. Okay, so extension we know is how far we are going to be moving this band or how far we're going to be compressing a spring. Okay, but the spring constant is going to be the force per unit of a specific material, okay, or a specific string. So when it comes to a rubber band, when it comes to a metal spring, when it comes to a plastic spring, the spring constant is going to be different. Okay, again, it's a constant, so it's a constant number for a specific material, but different materials and different springs or rubber bands are going to have different spring constants. Okay, and that's usually going to be given to you, or you'll have to work it out when they give you the potential energy. okay, and you'll have to maybe measure the extension. Okay, now we've looked at work. So work is going to be the transfer of energy, right? But power is going to be the rate at which that energy is transferred. Okay, so then we can also look at efficiency. This is the percentage of the total energy that is transferred into useful energy. Okay, so wasted energy would be your friction, your heat, your sound, something like that. So power is going to be energy divided by time. Okay, so it's the rate of change of energy. Power can also be work divided by time, and your percentage efficiency would be your output divided by the total multiplied by 100 because it's a percentage. Okay. So how can we increase the efficiency of something is by losing less energy to friction. Okay. Now, or less energy to the environment, let's say. So the first way is by reducing friction. So this is by adding something like lubricant or grease, which is a lubricant, I guess, to machinery. Okay, this is going to prevent it from heating up and losing energy to the environment through friction. Okay, the next is wires. Okay, so certain wires and certain materials that wires are made out of will have less resistance to the flow of electrons. Okay, something like gold is a very good conductor of electricity, even more so than copper. Okay, so a lot of things like speakers, high-tech speakers, use gold-plated wiring. Okay, so that there's as little resistance to the flow of electrons as possible. Another one is air resistance. Okay, so we know our cars shouldn't, some of them are. They don't look like boxes. Okay, they're normally streamlined. Okay, if you open up all your windows on the highway, it's going to eat your petrol super quick because you're increasing the air resistance. Okay, so by making something streamlined, there's going to be less air resistance and it's going to be more efficient. And finally, sound. Okay, so some machinery causes a lot of sound, okay, and vibrations. So what we do instead is we're going to dampen that sound, or by putting something like soundproofing, or as I say, cladding. So having rubber feet on the bottom of a washing machine, let's say, will reduce vibrations and sound, thus making it more efficient. Okay, my name is Cameron, and I'll see you in the next video.